All right, good morning, grade 12s. Today we're going to move on. We're going to talk about kinetic energy. That's going to be our lesson for today. It's a very brief lesson. It's only one page of notes, two examples. Should go pretty quick. I will probably find a way to make it take a little bit longer somehow. That's what I tend to do on these. But we are going to do a problem of the day as well, obviously. Physics never stops. You know that. So today, a pretty wild day of the year. Today is National Unicorn Day. It is also Cherish an Antique Day today. We've got a combination here, Cherish an Antique Day and Unicorn Day. So an antique clock is being pulled by a unicorn 4 meters along the floor with a force of 150 newtons, 35 degrees above the horizontal. What work has been done by the unicorn pulling the clock? What happened to my animation there? There we go. Pulling the clock. All right, so unicorn pulling an antique clock. How much work has been done by the unicorn? So pause the video now, work on that question, and then when you come back, I will go through the answer. All right, welcome back. So the answer is the work is equal to the force in the x direction multiplied by the displacement in the x direction, which would be 150 cos 35 times 4, which gives you a total amount of work of 491 joules done by the unicorn. 491. And what are my sig figs like here? Don't worry about it. All right, so should have rounded my answer there to 490. But when I made these, I was not thinking about sig figs. That was last year's problem. All right, so let's move on. We will do the notes for kinetic energy now. Reminder, if you're watching this, you probably won't actually have time. But on Thursdays, I'll be doing live meetings. So if you are struggling with some of the concepts, just tune in on our Google Meets on Thursdays. We have one today. But by the time I get this posted, you probably won't have time to watch this and then tune in. All right, let's get started. So let's share a window. Kinetic energy. What is kinetic energy? Let's do some different colors today. All right. What is kinetic energy? Kinetic energy, I usually refer to it as KE, but you can also do it as E with a subscript K, totally fine. It's the energy resulting from motion. So it's the energy that is stored within an object because it is in motion. And it's calculated as follows. KE is equal to 1/2 times the mass of the object times the velocity of the object squared. So 1/2 mv squared. Normally, I would write out what everything is. In this case, you know what? I'm being lazy. Let's just do it. Mass is m, v is velocity, and ke is kinetic energy. Energy due to motion. What do I measure energy in? You got it. Joules. Now, a transfer of energy, we learned this yesterday. A transfer of energy can also be called work. So work, we talked about, could also be called a transfer of energy. When the kinetic energy of an object changes, that object is going to either have its energy transferred to another object or it will have received energy from something else. This is due to the law of conservation of energy. Energy cannot be created or destroyed. It can only be transferred. All right, we'll learn about this. But this change in kinetic energy is called work and be calculated as follows. Work can be seen as the change in the kinetic energy. So work, W, can be seen as delta KE. What that means is that work can be seen or calculated as the final kinetic energy, let's call it KE2 or KEF, up to you, minus KE1 or KEI, initial. So just a side note here, it's important to assume in this question that the height of the object was not changed. Okay, the height of the object was not changed. That means that we only have a change in energy in the x direction in this case. All right, so let's do two examples. Like I said, it's a pretty brief lesson today. A 100-kilogram man is in a car traveling at 20 meters per second. Find the kinetic energy of the man. So mass is 100 kilograms. The velocity is 20 meters per second. And our formula, we're trying to find kinetic energy, KE, let's say, we're trying to find kinetic energy. The formula is 1/2 mv squared, or 1/2 m, which is 100, times v, which is 20, squared. And if I calculate that, I should get KE is equal to 20 squared times 100 divided by 2 should give us 20,000 joules. So there you go. There's our final answer for the kinetic energy of the man within the car. Now, not a good scenario. The car strikes a wall, comes to a complete stop after the car collapsed 1 meter. Find the force exerted by the seatbelt that the man is wearing. This is a bit trickier. But let's take a look at a couple key pieces of information in the question here. Car comes to a complete stop. That right there is telling us that the final velocity, v2, is going to be equal to 0. Right? This right here, it collapsed 1 meter. This is a hidden way of telling us the displacement is 1 meter. Right? That car moved another meter before it came to a full stop. And we have to find the force exerted by the seatbelt on the man that is wearing it. This is an application of our second formula that we learned here. This is an application of work is equal to the change in kinetic energy. We went from moving to not moving. That's a change in kinetic energy, right? If I think about what my kinetic energy initially, it was 20,000 joules. Well, if I have V2 as 0, that means that my final kinetic energy is going to be equal to 0. So let's write that out. Work is equal to KE2 minus KE1. Well, because of this, KE2 is equal to 0. But I'm not trying to find work. That's the thing, is I'm not trying to find work. And we saw that here. We're trying to find force. How is work related to force? We did this in our problem of the day today. Work is the force multiplied by the displacement. And KE2 was 0. And KE1, we already know the initial velocity of the car was traveling at 20 meters per second. So it has an initial kinetic energy of 20,000 joules. So now all of a sudden we have a nice little setup here. We have F delta D equals 0 minus 20,000. Well, this question gets even easier because what is delta D? Delta D is just equal to 1. So this becomes F times 1 is equal to negative 20,000. So what we're basically saying here is that the force exerted by the seatbelt, let's give it a direction, is 20,000 newtons, but it's in the opposite direction. I'm going to say backwards. So if we know the car was moving forwards, then the force exerted by the seatbelt is going to be 20,000 newtons backwards. That's a lot of force, obviously. Not ideal to be driving 20 meters per second and run into a wall and come to a complete stop after 1 meter. You're going to feel a lot of force. Okay, this is kind of this is related to our impulse and momentum concepts, right? You want to increase the amount of time it takes to stop. Therefore, you feel a smaller force. Let's do one last example. A baseball is thrown and the velocity diminishes from 20 meters per second to 15 meters per second. If the mass of the ball is 0.15 kilograms, how much energy is lost? So let's write down everything. How much energy is lost? How much energy is lost? Okay, so we're trying to find the amount of energy lost, which we know that there's going to be a change in energy if we have a change in our velocity. So technically what we're trying to find here is work. We're trying to find that transfer of energy. The mass of the ball is 0.15 kilograms. The final velocity of the ball, or V2, or I'm using V2 today. You can use VF still if you feel more comfortable with that. Well, it went from 20 to 15, so 15 meters per second. V1 is, it was initially going 20 meters per second, so it slowed down. That's all the info we have. But thankfully, that's all the info we need. W is equal to the delta KE. It's equal to the change in the kinetic energy. So we have 1/2 mv2 squared minus 1/2 mv1 squared. Right? This just comes from KE2 minus KE1. All right, so let's write it all out. 1/2 times 0.15 times 15 squared minus 1/2 times 0.15 times 20 squared. If I do that, I should get, you can try plugging that all into your calculator, you should get negative 13 joules. So that means that it lost 13 joules of energy. Okay, so there is our kinetic energy introduction. In our next lesson, we'll be looking at potential energy, gravitational potential energy. And then moving onwards after that, we'll look at how energy transfers between the two of those. Start talking about roller coasters, stuff like that. All right, that is it for today. Have a great weekend. We'll see you later.